Hello everyone. So we're going to go through practice worksheet 17, and throughout the entire process of this, I'm going to be explaining the thoughts and rationale behind each of these reactions. Bear in mind that some of these reactions will use non-specific reagents, while others you will have to use very specific reagents for these specific reactions. So with that in mind, let's start out with number 1, which shows us starting from this alkyl bromide and ending up with an ether. The first thing that you'll notice here is that the stereochemistry that's on this carbon disappears at the very end. To be fair, this carbon is achiral in the first place, but it's worth noting that stereochemistry is gone. The other piece of information that you'll notice is that this is a tertiary carbon with a leaving group. With bromine as a good leaving group on this carbon, and it being a tertiary carbon, in order for us to actually substitute on this ether, because bear in mind this is the group that is being substituted on, we would have to be doing an SN1, because only in the SN1 would we be able to substitute on a tertiary carbon. Keep in mind that anytime that we're using things like primary carbons, we're going to be wanting to do SN2s to substitute, but tertiaries are going to be SN1s. So now I have to think, what is good SN1 conditions for this given reaction? Well, considering the fact that we need to add on this methoxy group here, the key piece of information is we need to have the methoxy as a weak nucleophile in order to actually do the SN1. So in this situation, if we have MEO, so the methyl with the oxygen, that would be, if it had a negative charge, a strong nucleophile. A good way to make strong nucleophiles into weak ones is just to add a proton on there. So methanol would be the nucleophile that we would choose for this given substitution. And now all we have to do is add in a temperature. Bear in mind this temperature can be anything we choose for it to be. SN1, of course, can occur at relatively low to moderate temperatures, so let's just say that we called this 30 degrees Celsius for the sake of it. And as long as this is SN1 conditions, we're good to go. So that would be the first answer to that question. Let's talk about the second one. In this second example, we see that we start from an alcohol, and we end up with an alkene. Now, anytime you see an alkene in these products, the first thing that you should think of is that alkene equals elimination. This is because at the moment, this is the only way we know how to make alkenes. So, in the case of an elimination reaction, that would tell us that no matter what it is, we need to have a good leaving group. At the moment, on our starting material, we have an alcohol. This is a bad leaving group. So in order for us to do the elimination, we need to first convert the bad leaving group alcohol into some type of good leaving group. Now, as a reminder, we have 3 different ways that we can do this. We can either do a tosylation, use a strong acid, or do a halogen substitution. In this example, it should not make any difference because the stereochemistry of the alcohol will not play a role in the second reaction that we do. To show this off, what we're going to do is we're just going to do a tosylation. So we're going to say step 1 will be tosyl chloride along with a amine base such as triethylamine and DCM. So after step 1, what we would see here is that we would generate the tosylate leaving group, and the stereochemistry is going to remain unchanged. The reason the stereochemistry doesn't matter is because this elimination right here forms a monosubstituted alkene. Since this alkene ends up being the least substituted possibility, because notice that when we look at our leaving group, the alpha positions to this leaving group are either one that is a tertiary carbon, that would give us a tri-substituted alkene, or the one that we see actually forms the monosubstituted alkene shown below. So in this example, a monosubstituted alkene typically tells us that this is not E1. Because remember, E1 will always form the most stable, most substituted alkene possible. So if we wanted to actually do this and get that least substituted alkene, we need to do an E2 reaction. To be more specific, we need an E2 with a Hofmann base. Because remember, the Hofmann product is the one that is the least substituted alkene. So a Hofmann base, we know, has to be very bulky. So let's go ahead and choose that and actually write down our conditions. So for the second step, we need a strong, bulky base to do this E2. In this example, I'm going to say let's use tert-butoxide. So we can't actually just add it in as an oxygen with a negative charge. Instead, it has to come with a counter ion. So that's going to be, of course, something like a sodium, which can act as a spectator ion in the actual reaction. In addition, we're going to need a solvent and some temperature. So when we look at this here, we would say that we could use something like tert-butanol as a solvent, but you could also use any other solvent that you'd like that works with an E2. So for example, something like THF could also be a common choice, because at the very least, THF is a polar aprotic solvent, which also works well for E2. This, of course, can also be paired with a good temperature. So in this example, we can use a moderate temperature, something like 50 degrees Celsius. Again, the temperature doesn't matter an absolute ton, but it's still useful to put it there. And so that'll give us that alkene and should give us the answer to this question. Let's look at C. In this example, we see that our leaving group, which is this chloride right here, actually is on a carbon that doesn't end up in our product alkene. So notice that the alkene, if we were to label these carbons with some colors, is not on the orange carbon. Instead, it is between the green and the blue carbon. In an example where the final functional group that is formed is moved from the location of the leaving group, we need to start thinking about rearrangements. So in this example, I would say that we are seeing a rearrangement occur. Now, with rearrangements, this immediately tells us that this has to be SN1 or E1. But of course, given this is an alkene that we are forming, it must be an E1 reaction. So in this example, I would say that's exactly what we can do. So we need to put down a weak base at high temperatures in order to get that elimination reaction to occur. So something like H2O at 100 degrees Celsius would make this reaction happen. Just as a note, the reason this occurs is due to that hydride shift, because when our leaving group leaves in the first step of this mechanism, we end up forming a secondary carbocation. This secondary carbocation can undergo a hydride shift from the adjacent carbon in order to form a tertiary carbocation. And of course, that tertiary carbocation is where the reaction actually takes place in order to form the most substituted alkene, which is the one shown on the right. All right, let's look at D. So in D, immediately we see that we have a good leaving group and we end up with a ether there. So you may immediately think this has to be a substitution, and I would agree. However, you'll also notice that in this example, the bromine starts on a wedge, the oxygen ends on a wedge. What this tells us is this is a retention of stereochemistry. And of course, in our hands, we do not have any reactions that actually retain stereochemistry. So something like an SN1 would give us a racemic mixture. That doesn't retain stereochemistry, and SN2 only inverts stereochemistry. So if we wanted to retain stereochemistry, we'd actually have to do two inversions. We would have to invert once, so doing one SN2 to change the wedge to a dash, and then we'd have to do a second SN2 to change that dash to a wedge. So overall, this means that we need to do two SN2 reactions. So now we need to think about what can we do for the first SN2 that will give us a good leaving group that we can use for the second SN2. Right now we have an alkyl bromide as that substituent. So how can we substitute on a good leaving group while also having it be a strong nucleophile? Well, one really good way of doing this is using iodide. As a reminder, something like sodium iodide gives us an iodide nucleophile. So that I- is able to actually do an SN2 reaction to kick out the bromine in this case and give us the substituted alkyl iodide where the iodine is on a dash. So in this scenario, whenever we're using sodium iodide, as a reminder, sodium iodide is more nucleophilic in polar protic solvents. So something like ethanol is typically used in a step like this. We would also say that, in terms of temperature, this should be running at a moderate to high temperature. So we're thinking somewhere around, once again, 50 degrees Celsius works out pretty well. The second step of this reaction now is we need to do the other SN2. For this SN2, we can use the nucleophile that we care about, and so again, it's going to be essentially like methanol, because notice that we do end up with this methoxy group here, but we also do need to make sure that it is a strong nucleophile, so using something like sodium as a counterion is a good idea here. With SN2s, with something like methoxide, this of course does need a polar aprotic solvent, such as THF, and again, we can heat that up to about 50 degrees Celsius. So this right here will give us two SN2s, where the first one does the wedge to a dash, and the second one, whenever we use our methoxide, will displace the iodide and turn that dash into a wedge. And so that's how you do that problem. For the next one, this one's pretty tricky because seeing it is a little more difficult. The one thing that you'll notice between these starting materials and products is that we have two changes in terms of our leaving groups and nucleophiles that are present on the molecule. First of all, we'll notice that there is a alcohol group here, which is somehow replaced by a thioether. We also see that there is a bromide here that is replaced by an oxygen. The problem here is whenever we look at these, we notice that both are actually inverting in stereochemistry. So, practically speaking, that makes us immediately think that we must be doing SN2s on each center. Oops. But here's the thing. If we were to try and do an SN2, what you would notice is that we can't actually immediately do an SN2 in this situation. If we were to do the SN2, we would find that this carbon is a tertiary carbon. So even if we made the alcohol into a good leaving group, that doesn't mean that the SN2 would even be possible here. The other thing that you'll notice is at the moment we have a weak nucleophile in the form of this alcohol that is adjacent to a good leaving group. This is actually a good setup for an intramolecular reaction. The question is, does this make sense? Well, if we think about the intramolecular reaction that can occur, the best way to get to that product would be through something like an epoxide. Because as a reminder, we can invert stereochemistry that is on epoxides. So if we were to think about this as going back a step, we would say that if we had an epoxide where the oxygen was on a wedge, and this methyl group here was on a dash, the addition of something like an acid, where we do an acid-catalyzed epoxide ring opening, would give us an inversion of stereochemistry there, and you'll also notice that it would give us the alcohol on the carbon that we needed. So overall, what we want to do here is we actually want to first form the epoxide and then open the epoxide. In terms of forming the epoxide, when we have this alcohol and this bromine in the same molecule, we can do this by first making the alcohol a very strong nucleophile. So to do so, acid-base chemistry is going to help us. Deprotonating the alcohol, giving it a negative charge, makes it a strong nucleophile. So by using something like sodium hydride, this is a very strong base, it'll deprotonate that alcohol and make it a good nucleophile. Of course, this has to come with some type of polar aprotic solvent, because by making the alcohol a strong nucleophile, it can then do the SN2 backside attack to kick out the bromine. Heat this up to something like 50 degrees Celsius, because it's a good number, and you should see the SN2 occur. This, of course, makes the epoxide that's shown on the right. From this epoxide, in order for us to open it, remember that we need to do an acid-catalyzed epoxide ring opening, alongside having the nucleophilic sulfur. So what does the acid-catalyzed epoxide ring opening look like? Well, we need a strong acid, such as H2SO4, and it needs to be in the presence of that thiol leaving group. So that'll be the weak nucleophilic methyl thiol. So with this, we just need to give it a small amount of temperature, not too much. This could honestly go at about 30 degrees Celsius. And so that will open up that ring while inverting the tertiary carbon stereochemistry. All right, let's take a look at this next one. So in this example, we have a bromide on our starting material, and we have an alkene at the end. Bear in mind, this alkene immediately gives us the hint that this must be an elimination reaction. However, for this elimination reaction, if we think about it as either E1 or E2, the question is, which one do we pick? Well, in this case, they're both forming the most substituted alkene. That's the tri-substituted alkene that we see there. So both E1 and E2 are completely viable. However, you'll also notice that if we're talking about something like E2, we have to focus on where the hydrogen is that is on that other carbon that we're actually deprotonating. And on the alpha carbon, we do see that that hydrogen's on a dash. It needs to be anti to our bromine, but since we're in a ring, we cannot rotate that. So in this example, the E2 reaction that occurs actually would not form the alkene shown on the right. It's impossible since the hydrogen is not anti to the bromine. So this has to be an E1 reaction. With that in mind, since it has to be E1, it's very simple conditions. We can do H2O at 100 degrees Celsius, and that will give us our final product alkene without much of a problem. For G, we start out with a ether in this case, and we end up with 2 thioethers. What you'll notice here is that when we're thinking about this reaction, we start out with a cyclic version of the ether, and we end up with an acyclic molecule. If we number our carbons here, we can see that this is 1, 2, 3, 4, 5, and 6. We can see over here, this is 1, 2, 3, 4, 5, and 6. So in this scenario, we are actually going to be cleaving the ether in order to install our thiols. So the first thing that we can actually do is we can think of this in terms of the ether cleavage. What happens when we actually break open this ring? Well, in this scenario, let's try it out. If we use something like HBr with H2O and a large amount of heat, so say reflux, that is the conditions that will break open our ether. Here, if we were to break open the ether, what we end up with is a straight chain of 6 carbons, 1, 2, 3, 4, 5, and 6. And on either end, we've now installed bromines, because remember when we cleave these ethers, we kick off the oxygen using the bromine groups. We'll also notice that carbon number 4 has been rotated a little bit just for our straight chain, and so we do need to maintain the stereochemistry there with a wedge. If this is a bit confusing to you, you can also label this using R and S. Notice in the starting material, if we look at the chirality of that carbon center in the absolute configuration, we would say that this side would be 1, this would be 2, this would be 3, and so it looks like it's R, but it is S. And so in this scenario, we should see that the stereochemistry has not changed when we open up that ring. So once again, looking at that carbon, we see this is 1, this is 2, and this is 3. It looks S since that's on a wedge. It is S. So that's why this thing is on a wedge once this epoxide actually breaks open. We now have 2 leaving groups in the form of these bromides. Of course, in the case of these 2 reagents, we see that the bromine and the bromine must be replaced by the thioether and the thioether. So how do we do that? Simple SN2 actually works in this case. So for our second reaction, since these are both the same nucleophile, we just need the sodium thiolate, and keep in mind that we're going to want to use 2 equivalents. I did forget to say for the HBr shown up top, that does need to be in excess in order to replace both of those bromines. So we do need the 2 equivalents of the methyl thiolate here, alongside a polar aprotic solvent. Something like THF is always nice, and some heat will suffice, 50 degrees Celsius. For this question here, we have an alcohol right here that is a good or a bad leaving group, and we end up with a nitrile, which is a little uncommon. But typically when we've seen nitriles in the past, these have come from a precursor molecule that has been something like an alkyl bromide. Because as a reminder, from the alkyl bromide, we can just do an SN2 using sodium cyanide, NaCN, in order to reach that product. So the real question about this one here is, how do we make the alcohol a good leaving group? Well, we can use any of the methods above because it's on an achiral carbon, and therefore it doesn't matter what method we use, since the stereochemistry doesn't have to be specific. So in this example, I'm just going to choose to use thionyl chloride, so SOCl2 will replace the alcohol with a chlorine. Then the second step of the reaction can be that SN2 with sodium cyanide. So there's the NaCN. This can be done in something like a polar aprotic solvent. Let's mix it up a little bit and do DMF. And then typically this is run a little hotter, so let's say 70 degrees Celsius. And so that's how we would substitute on that cyano group. All right, for this one here, we see that we have an example of starting out with a non-ether and cyclizing into an ether functional group. Now notice anytime we're doing a cyclization, this must be some type of intramolecular reaction. And since it's going to be an intramolecular reaction, we essentially just need to make sure that we are doing the appropriate steps to make that intramolecular work. One of the problems with this one that you'll notice, though, is that we have a tertiary leaving group here, along with a primary leaving group over here. And anytime we have a situation like this, we have to treat them both a little differently. It's not like we can just use SN2 to form this ring. Instead, we have to substitute one of them and then substitute the other. First thing we need to do is we need to get an oxygen installed that can actually do the intramolecular reaction. I'm going to choose to do this via an SN2 reaction on the primary alkyl bromide. So something like sodium hydroxide in something like, once again, THF at a relatively, low temperature, such as this here, will get us to that first product. So this product, of course, after step 1, would be the displacement of the alkyl bromide. So from here, what we can do is we can say, in order for this to do an intramolecular reaction, on this tertiary group here, it would have to be something like an SN1. So our second step, we can just do SN1 conditions. H2O at, once again, we'll say 50 degrees Celsius. Because in this scenario, the formation of the carbocation by the tertiary bromine leaving would allow the alcohol to come in, do the attack on the carbocation, and form the ring. So that's how we come up with that answer there. It's an SN1 followed by an intramolecular, it's an SN2 followed by an intramolecular SN1. For J, we are somehow replacing this oxygen and this ether with a nitrogen. Now, for this scenario to actually work, there's a couple things that we need to keep in mind. So the first thing is, this oxygen on its own is just a bad leaving group. So it's not like we can immediately replace it with a nitrogen. Instead, it's going to be more useful if we can replace it with good leaving groups and then substitute a nitrogen. The other thing that you need to remember for a question like this is that nitrogen on its own is considered a strong nucleophile, which means it's really good at SN2. So the only reaction we know of right now that can break open ethers is the ether cleavage. So using something like HBr, in this case in excess, along with some H2O at reflux, would give us the opened ring where we would have 4 carbons, the 1, 2, 3, 4, with bromines on either end. Now that we're here, we can say, well, we need to get that nitrogen installed. We can do that using the fact that that nitrogen on its own is a strong nucleophile. So if we use something like methylamine, which is this methyl NH2, what we would see happen is that the nitrogen could attack and kick off one of these bromines, and this could be followed, once we've installed that amine, it'll have a positive charge. This can be followed by a deprotonation by another molecule of dimethylamine, or of just methylamine. And then another one that follows is going to be the nitrogen of the original methylamine is now a good nucleophile that can actually come in it can attack and kick out the other bromine. And so here you can see how the nitrogen actually ends up in that ring system. Because that intramolecular reaction gives us that 5-membered ring. And now an additional molecule needs to actually deprotonate this. If we were to say it's dimethylamine, that would work just fine. The other thing we can do is we can replace these dimethylamines with other bases, because keep in mind that it doesn't necessarily have to be this exact molecule acting as a base. So what we'll do here is we'll say that we're going to use methylamine as the nucleophile, and then I want to use a base that's not really a nucleophilic base. Something like triethylamine would work great, because this does the same thing that we had talked about previously when we had done tosylations. It just acts as a base to deprotonate that product. And then, of course, this needs to be done in some type of solvent. Let's say, in this case, DCM, at a reasonable temperature. We'll say 40 degrees Celsius. And so that ether cleavage followed by the SN2 that's intramolecular is the best way to do that one. All right, so for K, we start out with an alkane. Anytime you see an alkane as your starting material, keep in mind there are no specific reactions we can do on this except for one. This tells us we must do a radical halogenation. Well, radical halogenation is done using something like bromine, Br2, with some light, that H-nu, and a solvent such as CBr4. This, of course, will install a bromine on one of the tertiary carbons of our reactant. And so the bromine would end up right there. This is a perfect pathway to reach our product, because notice in our product, the bromine is being substituted for this large ether group here. This is an example of something that has to be an SN1, because keep in mind that our bromine right now is on a tertiary carbon. So since this is an SN1, we would say that we need the weak nucleophilic version of that alcohol alongside some temperature, let's say 40 degrees Celsius. So that would give us the product that's shown there. This last question takes it a step further. We not only end up in a situation where we have the starting material as an alkane, but we also end up with an alkene and a substitution with an ether group. So there's a lot of things to keep in mind here. Thinking about what we can do in this situation, it's easiest to start with something that we know, because we can guarantee that since we start out with the Br2 as our radical halogenation reaction, that must be the only thing we can start with since we start with this alkane. Reaction 1 in this scenario would generate this alkyl bromide. Now we have to ask ourselves, what reaction makes the most sense in this case? Technically, there are two possibilities. Possibility number 1 is we do the substitution right now. This would install our ether onto that tertiary carbon, and then we'd be good to go. Or we can do an elimination. The question is which one makes more sense to us. Well, in the scenario of doing the elimination last, so assuming we do the installation of the ether first, we would need to have a situation where we install the alkyl bromide on that secondary carbon. This is not completely unheard of, but since radical halogenations don't usually happen very well on secondary carbons or primary carbons, that may not be our best option. However, if we do the elimination first, what'll end up happening is we can form the most substituted alkene in this case, which would be in a position where we can actually do resonance on the next radical halogenation. Notice that if our radical ends up on this carbon over here, a resonance form can be shown that actually puts the radical onto the tertiary carbon. This would allow us to still install a bromine there, and we'd also get the benefit of having our alkene on the terminal part of the molecule, which is exactly what we want. So in this scenario, I would say that's what we want to do in that step. We want to do a radical halogenation to not only move the alkene, but end up with our alkyl bromide exactly where it needs to be. This, of course, can be followed up with a fourth reaction, which is just the substitution to install the ether. So, with that in mind, let's think about what we can do to actually make that second reaction happen. We can do it either via E1 or E2. In this case, I'm going to say let's do it via E2. We'll use sodium amide, NaNH2, as our strong base, alongside something like DMF as our solvent, and some high heat, say 80 degrees Celsius, to ensure that we get that elimination. The third reaction is going to be the same as the first. It's just a radical halogenation. This time, we just see that resonance form actually makes a difference. And then, of course, our final reaction is going to have to be using methanol, because we're trying to do an SN1, because bear in mind our leaving group at this point is on a tertiary carbon, so we can't do an SN2. So methanol works well at a pretty low temperature, because this is going to be a fast SN1, so we can do something like 20 or 30 degrees Celsius. And so that's exactly how you take on all these problems. Hopefully this was beneficial for understanding this worksheet.